what I want to discuss today is this idea which is going to mix information theory in the quantum world with thermodynamics. So it's really a kind of a tale of two realms. You have, the macroscopic world that we live in, which is governed by thermodynamics, and you have engines, you have refrigerators, and that kind of stuff. And then you have the quantum realm, composed of atoms and very small particles. And what I want to tell you about is how we can connect these two realms and what kind of cool things we can make with that. So let's start with thermodynamics. So, this is a little bit cut, sorry about that. But there are two laws of thermodynamics that are the most important ones, the first law and the second law. Now, the first law is essentially about an energy budget, right? It's the idea that energy is something that's conserved. You can convert it, change from one type of energy to another one, but eventually you always have an energy budget, which means that you need to keep track of every source and sink of energy that you have. So for example, you can convert energy in a steam engine, which takes heat into work. You can convert chemical energy into heat, like in the combustion engine, for example, or you can convert mechanical energy into electricity using Faraday's law. You can, of course, store and retrieve energy in terms of battery, nuclear material, and so on. And in these processes, you always have losses. But you keep track of your energetics. You keep track of every source and every sink of energy. Okay, but what about the second law? So the second law is different because it tells you that there are certain processes that cannot happen. So even though the first law just tells you that energy has to be converted from here to there, but it doesn't place any restrictions on what can and cannot happen. And the second law does. So here are some examples of things that the second law specifies. For example, the free expansion of a gas. If you have a gas which is in half a container and you open this door, then the gas is going to expand. And you'll never observe this the other way around. Right? You'll never observe this gas spontaneously compressing into one side of the container. The same thing is with the flow of heat. We know that heat flows from hot to cold, so energy flows from hot to cold. And we never see this the other way around. We never see heat spontaneously flowing from cold to hot. Right? And again, another example would be friction. We always have dissipation, and we know that the block is going to slide down. We never see the situation where the block just absorbs heat from the surroundings and then goes up. Right? So we know that there is there are processes that happen, and there are processes that don't happen. So here is a video that I like very much. So this is from George Porter. He was a Nobel Prize winner in chemistry. And he has a bunch of cool lectures on YouTube. And here's the video. So let me see if I can play it. Yeah. Okay, here we go. This is the video. Right? And then you can ask the question, was this video played backwards or not? Right? I mean, the answer is obvious. It was played backwards. And why was it played backwards? Because this is an example of the arrow of time, of this irreversibility that is associated to the second law. The second law says that there is an arrow of time, that time flows in one direction, that processes have a preferred direction. It's the same reason why heat flows from hot to cold. Now, how do we reverse this? How do we, change, reverse the arrow of time? One example is an air conditioner. An air conditioner is making heat flow from cold to hot, and we do that all the time. How do we do it? Well, we need to consume something, right? We need to pay a price. So if we want to make heat flow from cold to hot, we need to use, for example, electricity or some source of energy. So we use energy, we consume energy to reverse the arrow of time, right? So this is going to be the main point that I would like to emphasize by the end of the talk, that you can reverse the arrow of time. That's possible, but you need to pay a price. There's a cost to do that. And you need to consume something. You need some kind of fuel. What I want to discuss now is that when we go to the quantum world, the world of atoms and so on, there are new types of fuels that appear, which are not obvious in the macroscopic world. Yeah. Oh, I forgot to say this. Yeah, I mean, pretty much this is a saying that, there is no such thing as a free lunch. Okay, so now we come to the quantum world. So I will spend a few minutes introducing the basic ideas that govern quantum mechanics, and then we go to some of the applications. So quantum mechanics really started with spectral lines. Suppose you have some kind of gas in a cylinder, and you apply some kind of voltage to it, right? We know that this gas is going to emit light. We see this all the time. Maybe I can just forward a little bit. We see this all the time in these neon tubes, right? It's just there's some gas in here. We apply some kind of voltage, and it emits light. What is surprising, and this was discovered in the mid-19th century, is that the light that's emitted from this gas is not continuous, but is rather discrete. It's only emitted in a few specific frequencies or a few specific wavelengths. This is the spectrum of hydrogen, for example. It only emits in this wavelength, or this, or this, or this, period. You'll never find hydrogen emitting anywhere in here. And this is true for all materials, or all atoms. So this is hydrogen, mercury, and neon, right? And you see that each atom will emit in a very specific set of frequencies. So these frequencies, they serve as a signature for the atom in question, right? Each atom will have its own specific signatures. And this is, in fact, the way that we know, for example, what's the composition of galaxies far, far away. We know we just point a telescope to space, and we see that, the emissions that come in, they always come in these specific frequencies. So, for example, we can use this to know that there are no other atoms in the universe that aren't on Earth. The periodic table is complete. That's one way that we know about this. But this is very strange. I mean, this was perhaps in history the first kind of example of something that's discrete. All of our ideas in physics, they're always continuous, right? You can change things continuously as much as you want. So if you want to change the energy of a kid in a swing, you can push it continuously. If you can just push like infinitesimally a little bit, and it will change the energy by the corresponding infinitesimal amount. So everything that we do in our daily lives is continuous, and this is an example of something that's discrete. And I find that rather strange, right? The solution to this actually came in a very interesting case with Johann Balmer. He was a middle school teacher, and he was into patterns. He had no idea, what's the physics behind this, but he liked to look for patterns in things. And so he kept playing with these wavelengths of hydrogen, and he figured out, and I mean, this must have been quite a incredible discovery for him at the time, that if you plot 1 over the wavelength, then it's going to be some kind of number, which is called a Rydberg constant, but he didn't know that, but some number, and then a difference between 1 over 4 and 1 over s integer squared. And this is quite surprising, because it means that there is structure behind these numbers. They don't happen, like arbitrarily, but there's like some specific integers that you combine, and you give exactly these wavelengths. And I find this quite beautiful that he discovered it. Now, the solution to this problem came a little bit later with Niels Bohr. So Niels Bohr, he was from Denmark, and he completed his PhD, and he was also friends with the king of Denmark. And the king paid him to spend a year abroad in England, where he visited 2 labs that were working on these kinds of atomic physics. And essentially, Niels Bohr was trying to explain and come up with actually a microscopic model of this kind of behavior, right? But Bohr wasn't aware of Balmer's series. He was aware of the data, but not of this series. After almost 1 year in England, he became aware of Balmer's series by accident. And as soon as he became aware of the series, he writes that in his memoirs, that as soon as he became aware of this Balmer series, he was sure that this would be the good model for the atom. So Bohr proposed a model. And the model is that essentially the hydrogen atom has a proton in the middle and some electron that's orbiting around it. Very similarly to how planets orbit around the sun and so on, but with a very specific feature, which is that the orbits are not arbitrary. Either you're in this orbit, or you're in this orbit, or you are in another orbit, and so on. So the orbits, they are quantized. You can only be on a specific set of orbits. Anywhere else is prohibited by the electron. So the electron cannot be here. It can only be here and here, and here, and so on. And how does this explain the emission lines? It explains the emission lines because every time the electron jumps from one orbit to another, it emits radiation. So outer orbits have less energy, inner orbits have more energy. If you jump from outside to inside, then you emit a photon. Or if a photon comes in, you can go from outside to the inside. So you can emit and absorb radiation depending on if you jump between these orbits. Okay, so Bohr's model was, of course, not a very sophisticated model. In fact, we now know it's not really true. But it does give us a lot of insight into what is an atom. Maybe for us nowadays that is very obvious that we have an atom and we have an electron is a small particle, it's orbiting around the nucleus. But at that time it wasn't obvious at all. In fact, the most widely used model at the time assumed that the electron and the proton were actually like of similar sizes but kind of diffusive. So this was quite an achievement for Bohr. But then the big breakthrough, which is what we call nowadays the birth of quantum mechanics, came with Erwin Schrödinger in 1926. So this is the first sentences of Schrödinger's paper. And it's a quite interesting read. So maybe we can go through it. So in this paper, I wish to consider first the simple case of hydrogen atom and show that the customary conditions can be replaced by another postulate. So customary quantum conditions, he's referring to Bohr's model, this idea that you have orbits and you are only allowed to be in one orbit or another orbit and so on. So they can be replaced by another postulate in which the notion of whole numbers, the integers that we were discussing, they're not just introduced. So this is actually like a very severe critique to Bohr. He's saying, Bohr's model is you introduce these integer numbers and these integer orbits in a very arbitrary way, and I'm going to replace this by another postulate in which this notion of whole numbers is not just merely introduced. Instead, when it appears, when integralness appears, it arises in a same natural way as it does in the case of a vibrating string. So this was also Schrödinger's connection to this idea of wave mechanics, quantum mechanics as waves. And then this new conception is capable of generalization and strikes, I believe, very deeply in the true nature of the quantum rules. So this was Schrödinger's first paper. He produced a series of 4 papers almost in a row. And when he published this one, he already had a bunch of results for other papers. So he already knew that his theory worked. Before actually publishing the first paper, because he had done extensive testing. And so that's how quantum mechanics was born. It was born out of the desire just to describe the hydrogen atom. It's a very simple problem. You just have an atom, you emit radiation, and you want to describe it. But what came from it was actually a much more powerful theory, because quantum mechanics not only describes atoms, as we would like to, but it also describes anything that's made of atoms, which is everything. So everything from molecules, for example, comes from quantum mechanics. So one interesting example is maybe let me see if I have it here. Oh yeah. One very interesting example is Linus Pauling. So we all learned about Linus Pauling in high school and so on. Linus Pauling was a remarkable individual because he was a very clever person, but he was also in the right place at the right time with the right skills, with the right luck, and the right motivation. So he was really, right there. He was a person that understood chemistry very well, and he also understood physics very well, which is not always common. And he wanted to explain chemistry using physics, but he just didn't have the tools. And as soon as Schrödinger put his paper out, he just said, well, this is perfect. This is all I need. And immediately after 1926, Linus Pauling starts publishing one paper after the other, pretty much explaining all of chemistry, all kind of forces, chemical bonds, all of that, using quantum mechanics to explain chemistry. And then in 1932, only 6 years later, he publishes a textbook, which is still today one of the best textbooks in quantum chemistry. It's perfect. All of chemistry is described in there in a beautiful way, and that's just 6 years after Schrödinger's theory. quantum mechanics can also go in the other direction, and that's the direction of things smaller than an atom. Quantum mechanics can also explain the constituents of the atom, the proton, the neutron, the particles that make up the proton and the neutron, such as the quarks and so on. And it can also go to macroscopic objects, and I find this quite cool. The most beautiful example is superconductivity, right? So a superconductor is essentially a macroscopic manifestation of these quantum phenomena. And also, I mean, I have to say this, and this is very important, every transistor, right? So a transistor is really a consequence of quantum mechanics, right? The way that the transistor works is rooted in the rules of quantum mechanics. So it is safe to say, based on all of this, that we already live in the quantum age, right? Everything that we use around us has a quantum aspect to it. So quantum mechanics is everywhere around us and in every kind of technological application. But quantum mechanics is very counterintuitive. So there's this very famous quote by a physicist called Richard Feynman, which essentially, if you think you understand quantum mechanics, you don't understand quantum mechanics. So, you know, we'll never really understand quantum mechanics, and that's because it's a very abstract theory, is a very counterintuitive theory. And this kind of created a paradox, which is a funny one, because quantum mechanics is a very strange theory, but it's also super successful. And so people just didn't spend a lot of time trying to understand it so much, but just started applying it to solve problems and, you know, just explaining all kinds of phenomena using quantum mechanics, but not really bothering understanding the fundamentals of the theory. And so that actually, I mean, remained, for many, many decades, where there were very few people that were interested in really trying to understand why, what's happening to quantum mechanics. But that started to change, and it started to change around the 80s. In particular, with this notion of superposition. So superposition is a concept that was already proposed by Schrödinger. But around the 80s, people started thinking more and more about, you know, what does it actually mean to be in a superposition. So a classical bit is a thing that can be on 0 or 1, right? So it's either 0 or 1. Well, a quantum system can behave as a quantum bit or a qubit, which is simultaneously in 0 or 1. And this is already contained in Schrödinger's original result, but what does it actually mean to be in 0 and 1? I mean, does it mean that maybe it's in 0 or maybe it's in 1 and we don't know? Is it about ignorance? You know, ignorance in the sense that we don't know the state of the qubit, but if we knew, then it would be with certainty in 0 or in 1. So what does it mean to be in 0 and 1? And what it means in the end of the day is that it actually can be in two states at the same time. I mean, we now have experiments to prove this. The qubit is, when we say that a qubit is in a superposition of 0 and 1, it is literally in both states at the same time. And so this is interesting because it's like parallel computing, but by design, you know, because every kind of computation with quantum mechanics is already in parallel because they're always in superpositions of these different states. But there is something a bit strange, which is that if we measure the qubit, we only find it in 0 or in 1. So initially the qubit is in both, but then we measure, we only find one answer. And what happens is that this is related to the fact that when we measure the qubit, we actually change its properties. And we then define that the qubit will be in 0 or in 1. So before it was measured, it's in both. When we measure, it will collapse to either 0 or 1. Yeah?
Isn't it a philosophical question where it is if you can't measure it?
Mm-hmm. This is a very philosophical question, and it remained a philosophical question for many, many decades, until around 1965, people proposed experiments to test this. And I'll discuss one of these in a second, because, yeah, I mean, how do you actually test this? So I'll discuss one experiment where people proposed and was confirmed that actually shows that this is actually what happens. Okay, so it's already weird to talk about a particle that is in two states at the same time. But now what happens if we try to take this concept and discuss two particles? So suppose we have two particles, and we prepare them in what is called an entangled state. And if I may just write it here, an entangled state is something where you have one particle in 0 and the other in 0, plus one particle in 1 and the other in 1. So instead of having a qubit which is in either 0 or 1, we have two particles which are both in 0 and at the same time both in 1. So a superposition of 0, 0 and 1, 1. Now, suppose we take these two qubits, so we prepare them in this kind of state, and then we send them to two labs. So one lab in one city, another lab in another city, very far away. And in one lab, there is Alice, and she's going to make a measurement. So she's going to measure the first qubit, for example. If she does that, she can obtain either 0 or 1. But as soon as she measures the qubit, for example, if she obtains 0, then Bob's qubit is immediately going to go to 0. So initially, Bob's qubit could be in either 0 or 1. But as soon as Alice measures, his qubit immediately changes state, right? So this is very strange. So this is very strange because they can be arbitrarily far away, right? They could be one on Earth, one on Mars. And as soon as one particle is measured, then the other one will immediately be affected. So this was actually exactly this kind of experiment. It led Einstein in the 30s to put forth a paper criticizing quantum mechanics. So Einstein has a very famous paper saying, you know, quantum mechanics is great. It explains a lot of stuff, but look, this has to be wrong. This is, you know, it's just bugged. It cannot be like this. But actually, it is. So this is what happens. And in fact, this was the Nobel Prize just a few weeks ago. So the 2022 Nobel Prize was given for Alan Aspect, John Clauser, and Anton Zellinger. And exactly what they did was to experimentally prove that this is what happens. They, you know, made experiments where you prepare two qubits entangled. You send them to two labs, which are very far away, like literally like in different cities, so that they are, you know, sufficiently far away such that you cannot have any kind of subluminal communication, and then you measure this, and you can show that, you know, this is what happens. So this is one of the experiments which confirms that this is how nature chose to behave. It's still very strange. It doesn't give us any insight into why it behaves like this. That is very frustrating. We would love to understand why it can be like this, but we know for certainty that this is how it behaves. And one of the bad things about this is that even though this seems like you could use it for superluminal communication, you cannot. I mean, when you think about this, it would be awesome if we could just use this to send messages faster than the speed of light. But unfortunately, and this is kind of a technical detail, but it turns out that this cannot be used for superluminal communication. So that's kind of unfortunate. Okay. So this drive, to try to understand a bit better this notion of quantum entanglement, it led to where we are today and this idea of quantum technologies 2.0. We say 2.0 because, you know, a transistor is already a quantum technology, a laser is a quantum technology, so there are already loads of quantum technologies. But quantum technologies 2.0 are meant to be technologies that use entanglement and use these kinds of more fine principles of quantum mechanics. There are quite a few. The three most famous ones are sensors, communications, and computing. Quantum sensors is expected to be the first main technological gain from this new revolution in quantum mechanics. I'll show you some applications and some companies that are already using quantum entanglement to develop super high precision sensors for detecting all sorts of things. The next big main application is communication, so in particular encryption. So there's already one satellite that is being used to send quantum encrypted communication between different labs, and this is really could be a way of making encryption which is absolutely unbreakable. And then the next big one, which received a lot of attention in the last 4 years, is quantum computing. Quantum computing is essentially, you use, instead of bits, you use qubits. And this is expected to lead to significant gains in the way we can run certain algorithms. So there are a few algorithms that we expect should be much, much more efficient to run in a quantum computer. But quantum computing is kind of more into the future. It will still take a few decades before we can actually see this being useful in practice. So this is one example that I like very, very much of a quantum sensor. So there's this company called QSpin, which is making magnetic field sensors, which can detect magnetic fields with a precision that is unprecedented. For those of you who have worked with magnetic fields, the best way to detect a magnetic field is with a device called a squid. And a squid it has to run on liquid helium. So it only works at ultra low temperatures. And then you can get amazing precision. You can detect the smallest magnetic fields. This is better than a squid. It costs $500, and it runs on room temperature. So it's absolutely incredible, the progress that we made in the last 10 years in sensing magnetic fields.
You know what is the base?
It's an atomic vapor, so like a cesium vapor. It's similar to like an atomic clock. And then you just look at Zeeman oscillations and that kind of stuff. Yeah, so why would you want to detect magnetic fields? Well, this is a pretty cool example. So this is from the same group that developed nuclear magnetic resonance, MRI. So this is the University of Nottingham. And so this group, they developed MRIs in the, I think, 60s or 70s. And now they're doing something which is a little bit different. So they're using these magnetic field sensors not to take an image of your brain, like in MRI, where you take just a still image, but to actually make a video of your brain. So it's real-time video of the brain. And the idea is that every time there's a synapse of a neuron, it produces a super tiny magnetic field. And then if you just put like a bunch of magnetic field sensors in this helmet, so each wire here is one sensor, you can actually capture the brain in real time, each kind of neuron firing, and you can make a video of the brain. And this is super cool because, for example, there are certain diseases, such as schizophrenia, which you cannot see on an MRI. Like the brain of a schizophrenic is pretty much similar to the brain of a healthy person. Schizophrenia is more about the brain dynamics. It's about how a neuron fires and it propagates through the brain. And with this, you can now use you can use these magnetic field sensors to actually make a movie of the brain. And I think this could actually revolutionize medicine in the future. This I'm personally very fond of it. I think it's a super cool idea. Okay. So now I reach the last part of my talk, where I actually want to combine both things that I said. So I mentioned about the thermodynamic realm, the macroscopic realm, which is all about energy budgets and all about the second law, which tells you what you can and cannot do. And I want now to combine this with the quantum realm. So I wanted to discuss one paper that I'm particularly fond of, that was this collaboration that we did in Brazil about reversing the direction of heat flow using quantum correlation. So I mentioned before that if you want to reverse the arrow of time, for example, if you want to make heat flow from cold to hot, that's fine, but you have to pay a price. There's a cost, right? You have to use energy. Here's what we're going to do. We're going to show that we can do that not using energy, but using entanglement, using quantum correlations. So this would be the traditional setup where we have a hot system and a cold system. We put them to interact, and then they become of similar temperatures. What we're going to do is produce a system which has some degree of entanglement, so there are quantum correlations in them, and we're actually going to consume these quantum correlations to make the cold system colder and then the hot system hotter. So this was done in a nuclear magnetic resonance setup. So it's essentially a big tube which is cooled to very low temperatures, and there's a liquid inside which has a bunch of very special molecules. So these is a chloroform molecule, but it's special because one of the carbon atoms here is actually an isotope. It's a carbon 13, not a carbon 12. And the reason why we do this is because there's an extra neutron in the carbon, which acts like a spin and is going to act like a qubit. And there's also the proton in the hydrogen, which is also going to act like a qubit. So this molecule effectively produces 2 qubits. So it's like very similar to this kind of scenario where you have 2 qubits. And we can make them interact using a bunch of pulses of magnetic fields. So this idea, if I may come back for a second, of putting them in contact, we can actually reproduce this by using pulsed magnetic fields.
Can I ask you a question?
Yeah, of course.
What does it mean to be for a cold molecule, a single molecule?
Yeah. So
What does that mean? I mean, usually you think of cold and heat as into the agitation of the particle.
yeah, which is also true here. You're right. It's also true here because there's not a single molecule here. There's moles and moles of molecules in this fluid, and they're prepared using magnetic pulses. We prepared them such that the hydrogen proton is usually hotter, for all of them than the carbon. So it's exactly like we would.
What does it mean? I mean, what for a single atom to be colder or hotter?
It just means that, for example, that the probability of finding this spin in an excited state is bigger than the other one.
Okay,
So the thermal activation is bigger for one than the other. Okay, so here are the results. So this is energy of the cold system, right? So the cold system, in the usual case, this is the energy of the hot system, apologies. So the hot system, in the usual case, it should lose energy. And this is the green curve here. It starts here, and then, it just becomes colder. And this is the energy of the hot system. This is the energy in the correlated case. So you see that the hot system actually gets hotter, right? So while if they're uncorrelated, the arrow of time goes in the natural direction, where heat flows from hot to cold. In this case, at least up until this time, heat is flowing from cold to hot. And this is a measure of entanglement. So what's important here is that we're actually consuming entanglement to make this happen. If this guy goes up, then this one must go down. It's really a conception of entanglement. So we're using this entanglement to make this happen. And so what does this mean? Well, as I said, the second law, it's going to tell us that, which processes are allowed, and if we want to break them, we need to pay a cost. So what this says is that entanglement is also a resource. We don't need to use only energy. In thermodynamics, all of our resources are energetic. We burn fuel. We consume energy. In the quantum realm, we can actually consume a different kind of resource, and that's quantum correlations. This can be consumed to make this to make a thermodynamic test. Now you may ask me, is this practical? Are we going to build a device out of this? I have no idea. I mean, this is very preliminary. Maybe we'll never will.
So the question is, can you generate in time without energy?
Yeah, you can. You can. Yes, you can. Of course, there is no free lunch in the end, right? So it's just like with energy again. There is no. We cannot use this to make like a how do you call this in English? Moto perpetuum. Perpetual motion. Yeah. We cannot do that, of course. But we do have another resource. So, for example, we can, instead of storing a resource as energy, we can store a resource as entanglement and then consume that, just like we would consume energy in a battery. Yeah?
Classical correlation don't do the same?
No.
Similar? No.
No, so this can be proven. This cannot be done with classical correlations. It has to be quantum correlations. And that's quite interesting. And we can also show that it has to be consumed. So it's really something that is being used. It has to go down for the other thing to go up. So that can also be shown. So I think this is a pretty cool idea because it opens up a new possibility. It tells us that, if we go to the quantum realm, we can use the similar laws of thermodynamics, but with extra resources. There's extra tools for us to use. And that's pretty much what I wanted to say today. I think I'm done. So I just wanted to mention that, so I'm from the University of São Paulo, but I'll be moving to the University of Rochester soon. And we are hiring, so if anyone wants to discuss this, it would be a pleasure. But I think that's it. That's all I wanted to say. So thank you very much.